Thank you for coming. I'm going to present our work. It is a joint work between two Brazilian universities, and we have developed what we think is the first type inference engine for C. Let's get started. Let's try to get started. Oh no. Yeah, we have two, one with the laser and the other one with the switcher. So this is a complete C program. Why is it complete? Because you can just submit it to GCC or Clang, whatever C compile, and it produces object code, right? And this is an incomplete C program. It is incomplete because we don't know what T is. So if we try to compile that, we will get an error like T is unknown, T is undeclared, undefined, whatever. So we have a better definition of incompleteness in the paper, but for the purpose of the presentation, incompleteness is the name of a type that is not present in the program, like in this case, right? And complete programs are often useful, at least real-world programs. We want to make them useful, and, but why care about incomplete programs? Well, incomplete programs appear in a lot of places, like when you're editing, you're developing within an IDE, what you have is an incomplete program. In bug reports, when you submit that segmentation fault, or whatever, what you actually do most of the times, you don't paste the entire project, you submit a snippet, which is an incomplete program. In patches, unless you're doing the very first commit in your project, most other patches, they are incomplete programs themselves, or they change one line within a function, and then we consider that function as the incomplete program. Incomplete programs also appear when we're doing cross-platform development. Your Windows, and then you have to maintain or do some sort of analysis in a Unix, macOS application, and then you don't have that those components available Windows. So what you have is a program which you have most of the type definitions, but it's still incomplete due to the things that are not available in that platform. And incomplete programs are also, of course, in plenty of programming books in the snippets that teach you how to implement quicksort, and usually the entire driver and all the type definitions are not necessary in the same snippet. So incomplete programs are ubiquitous, and it is worth trying to understand them. Because if we understand the partial source code, we might be able to do interesting things with them, like reconstruct header files, which can aid development of cross-platform software, like the situation where I just mentioned. Or maybe you have your embedded device which runs some software that you want to analyze on Valgrind, and then you don't have those components on your PC platform where Valgrind is being run. And reconstructing header files can be an exit out of that. And this is an experiment we conducted with the tool we developed. The programs that you see here, they come from the GNU Coreutils, which is a quite popular a library in Unix and Unix-like systems. Those are sorted in alphabetically order. What we did here is that we removed all top-level declarations, which are struct definitions, type defs, even macros, and we reconstructed them, and we can still produce well-typed programs. And I don't have the laser here, and I don't want to get confused with two, but you can see that GCC, Clang, and KCC, which is now in the academia, it's a more rigorous compiler, and we do have warnings, and I'll explain a little bit about that later, but we can produce programs free from error, from compilation errors. So this is one reason why we might want to understand partial source code. Another thing that a situation where the understanding of partial source code can be beneficial is that we can enable static analysis tool to work in certain scenarios where they wouldn't otherwise. Many of those static analysis tools, they require build specifications and the actual entire compilation thing ready that you can run and they can search for the right headers. And many of them are available on Windows or Linux, they are not on Mac, so they have plugin mechanisms to put that stuff in a way that you can compile. But what if we can just take the snippet that we are interested on and analyze that snippet and still get the diagnosis that we would have gotten if we analyzed the entire program? I'm going to show you, this is from PVS Studio, is a well-known static analysis. We actually took their own snippets from the showcase, and for a category of diagnosis, that's of course not all sorts of diagnostics, we can just reconstruct the particular, this comes from CPython, the Python interpreter. This comes from NetBSD, and there are other in the paper. And we can construct, and the outcome of our reconstructor is still produce the same diagnostic results as we would by compiling the entire program. Well, understanding partial source code is also interesting if we want to just do some sort of fine-grained code reuse, because there's so many data structures implementation out there in cool projects you want to reuse, but then you want to copy that thing or part of that thing, but then there is one type and another type that is in the very topest header of the whole hierarchy, and then you see it goes crazy, right? Because it's a textual inclusion mechanism, and there's just no way out of that. But what if we simply infer the missing part from that algorithm, and you can copy and paste to your project, and it just works? Of course, might need to do some fine-tuning. So we took slices from implementation of typical data structures from libraries like GLib, which is GNOME-lib, GDSL, GNULib, and even from Sedgwick's books. And we can, again, reconstruct this out of the slice. We can reconstruct the type definitions that match them without errors. Of course, there are some subtleties when it concerns implicit conversions, and sometimes we can't restrict the type enough. So this is the data in the Inference column of the table. You might want to look into details in the paper. And understanding partial source code is also beneficial if we want to do software testing. A tool like PathCrawler, for instance, it generates input test data for our programs. But again, it requires build specifications. It requires the entire setup that you need to build. But this is a patch that went to the Git repository, to the Git project itself. It does a check in the commit, when you do Git commit, and it does some checks. This function was the actual patch there and the call to the function. What if we can just take that patch, which is like 10 lines of code, and generate input test data without having to compile the entire project that would be necessary? So we did that, we reconstructed only the struct that would be necessary, submitted it to PathCrawler, and it just generates the necessary input data that it would have generated if we had the entire program, right? So hopefully I have convinced you that understanding partial source code can be a good thing. And this happens, there's some work in other programming languages about understanding partial source code. So, but in C, this is challenging. There are some subtleties in C that make this word not straightforward as it is in certain other languages. I'm going to show you some of them. It begins with parsing, because in C, syntax analysis requires semantic analysis. And I mean, this is an ambiguous construct in C's grammar. Is it a multiplication? Or is it a pointer declaration of a pointer? Or is it multiplication? So we don't know that, right? Because if we only have the incomplete part of the code. Let's take another challenge. This is a semantic ambiguity, because 0 is an integer value. However, 0 is also the null pointer constant in C. However, pointers and integers, they are not interchangeable. We cannot unify them because they don't work under the same rules of the language. So is this a declaration of a type-def int pointer and we are initializing a pointer, or is it just a plain integer value that we are initializing with 0? We also don't know that information. Things get slightly more complicated when we start looking into type qualifiers like const. In particular, when we're dealing with pointers, let's see, in this case, we have a t1 here can be either int or const int because this is a value, this is a copy operation on values. It doesn't really matter if we assign int or const int to t. In this case, despite y being const, we cannot make t2 const. So there's some asymmetry here, even though the assignment is supposed to be equivalence relation. In this case of S3, it's similar, but now we have pointers. And even though w is a pointer to a const int, c cannot be made a pointer to a const int, even though it appears in our equivalence with w, which would be in theory lead to a unification of those two sides. And because we're dereferencing c right below. So if we would infer as const point, just like as w, we would have an error, right? And finally, this is the case where we actually want t4 to be a pointer to a const, because otherwise we would break the promise of constness that comes from z. So those are a few of the challenges that appear. Let's take a look at one more challenge. The ones that I'm showing are not necessarily all the challenges. They are the ones that we pick as the most interesting one. We described others in the paper. So we have malloc, malloc, malloc. And then what exactly does malloc return? Is it a pointer to an int, a pointer to a double, or whatever? We don't know. So malloc returns void pointer, and void pointer, as opposed to in C++, in C, void pointer casts to any other pointer type implicitly. So we have something to do here. We need to identify that those are pointers to a specific type. Okay, so those are the challenges. Let's see how we overcome these challenges. So this is our contributions right now. I'm going to outline the big steps that we do. To deal with the syntax ambiguity, what we do is that we postpone parsing decisions, right? We don't know what x star y is, so we continue parsing. We create an ambiguous AST node, and we keep going until we have information to do that. This is a technique that's not novel per se. IDEs and other tools do something similar. We have, however, a good formalization to describe what is actually going on with this. And about the null pointer thing, what we do is that we have a pre-inference stage, and the result of this pre-inference is what we call pre-types. I'm not sure it's the best name, but it's what we came up with. Actually, the name in the original paper was different. We had suggestions to change it. And what this pre-inference does is that it serves as a way for us to identify the use of those names in the entire program, so we know that they're actually a pointer or they're actually an integer value. So we produce constraints or type inferences based on constraint generation and then constraint solving. Eventually, we'll have constraints that will restrict the type of a particular a name that's appearing, so we know whether it's a pointer or whether it's an integer. This is probably the hardest one. That's the case of constness. What we do to deal with those asymmetries in the assignments is that we create subtyping relations. C itself doesn't have any sort of subtyping, but we introduce a subtyping here relation because what we have there is a sort of subtyping. The const cannot go to non-const, but the other way it is okay to do. But of course, this will pose a challenge to traditional unification, because unification is all about equivalences and make things equal. So we cannot use standard unification to do that anymore. And I'm going to show you how we do that, how we solve this. And the other challenge, when we don't have enough syntax in the program that restricts the type of variables, we use the concept of orphans, which is borrowed from Haskell. It's not exactly the same thing, but in some intuitive sense, you can do the mapping. And we treat void pointers as a top type. Again, there's a subtyping relation here. So let's take a look of a grammar which would be similar, a small grammar which would be similar to the C grammar. So X star Y is a production for the declaration of a variable and also for an expression. And this is the problem. We don't know which one when we are parsing the C code. But if we use a slightly improved grammar, where we have X star Y as a production for type or variable, and then we have a secondary step in which we use productions that are unambiguous to either put X or Y in the set of types or in the set of variables later on, then we have a disambiguation mechanism. And if we see, for instance, in this case, we are sure that X is a type, and we put X in the set of types. In the other case, we put X in the set of types, Y in the set of variables. Eventually, what we have is types in T and values in variables in V, and these sets must be disjoint, and we can disambiguate things. So this is a formal description of our disambiguation mechanism. This is our lattice of pretypes that I mentioned before. It consists of 5 elements. U, which is undefined. Everything that is not a scalar, and scalar in C means either pointers or arithmetic types, is in the bottom. Scalars comes right after, which is what we are particularly interested on. And then we have either numeric or pointer. And if the program is malformed, we have a top element there, which indicates the program is malformed. So in this case, when we see that A equals 0, we already know that it must be a scalar type, right? If we see a different a dereference, we know that we must be dealing with a pointer type. And this is the case where we have a dereference, and we also have a multiplication. Okay, and in C, pointers cannot appear in multiplication, so this programs takes our lattice to the malformed stage. And then the result, as the result, we have our pretypes defined. So this is what our constraints look like. So you can see here expressions in the C language on the right side, and how we produce constraints on the right side. So there is existential type variables. Eventually we instantiate those type variables. And it is pretty standard with one exception. So we have a table M, which is the result, which carries the information we have computed in that pre-inference stage from our lattice. And we need to use that information, particularly in 2 cases, in binary expressions in general and in assignments, because this is when pointers can interact with integers. So I can have a logical relation between a pointer and an integer in C. So in binary expressions and in assignments, what we do is that we make a consultation to table M, and we check what is the result, what is the pretype of that thing, the AST node in question, and if we have something inconsistent, we drop this constraint. Dropping the constraint here doesn't mean that we actually remove the constraint. It means that we simply don't generate a constraint for that expression. And an inconsistency means that we have on one side a pointer and the other side a numeric type. 2 minutes? Oh, so my clock is wrong. In assignments, we generate subtyping, and binary expressions, we generate equivalences. And we also rely on the C rules to refine the operands of result type. This is our constraints, the equivalence. The only important one is the subtyping relation. And I'm going to have to skip forward. I just realized, I'm sorry that my watch was not actually taking the time correctly. Those are pretty standard. The one that I want to touch is the subtyping relation. So you can see in assignments we generate subtyping relations there. And it is counterintuitive to think that we can take a pointer as a subtype of a pointer to a const, but it meets Liskow's principle in the sense that a pointer can safely be used in a context where a const pointer is expected. So we use a two-stage unification. First, we apply standard unification, just as plain usual nonce unification. Then we instantiate the types and we sort the type inequalities that we have. Eventually, what we have is a secondary unification stage, which is more elaborate and is qualifier aware. What we do is that right now we have things sorted as according to our partial order, which understand the const relationship, and we know that pointers need to be taken care of separately. And we see, when we see a pointer as a positive type, and here I'm using the terminology from Dolan and Mycroft, which is a paper from POPL last year. They deal with subtyping unifications. And if the pointer type appears a negative type, we discard the qualifiers, right? So there are other things that are interesting to do in the inference of C, like when we have orphans. There's an example, please take a look in the paper, what we do in the orphan case. Variadic functions, which we use the first unification error to detect where the variadic parameters appear. Arrays are treated in the decade of form of pointers. This doesn't impact the static semantics, only dynamic semantics. Decaying of function and function pointers, we also treat that by allowing these types in the unification. And macros. We treat macros as function or function object like macros are treated, and there is a workaround when the macro doesn't span to synthetically valid code, which I will also welcome to look at the paper. And this is the software. It's in GitHub. The source code is available. And you can also try our online interface, which you can simply paste a program there, and it should generate a reconstructed header file that makes the entire program compiles. Okay? Thank you.
Hi, very nice talk. So your lattice of pretypes basically gives you a way to reason about all of these possible, your pointer types, or numeric types, and then kind of see based on the use which one it actually is later. I don't know if you've heard of variational typing, but this seems very similar to it, where we could assign some kind of choice type between all of these different things, and then based on the use later, eliminate certain possibilities. And it also has like it's syntax directed, has nice unification and stuff. The only thing I don't know if it work with is what you do with the subtyping later. But have you looked into variational typing at all?
No,
okay.
Unfortunately not. I have to look into that then.
Okay, yeah, I think.
Thank you for the hint.
So it looks like the only interesting subtyping that is going on is at the qualifier level in your type system. Is that fair?
Yes, we only use, actually subtyping is the entire unification as a whole, but when it's used is when we're dealing with type qualifiers.
Do you have the need to think about higher order types at all, like interesting function types or object types?
Sorry?
Do you deal with function types at all in this language?
Yes, if you're talking about functions themselves and function pointers, yes, we deal with them.
And the qualifiers could appear nested inside these function types.
I'm not sure if I completely understood. Nested inside. Yes, if they're in the arguments, they appear okay. We don't have function calls in the micro language, but if you try our actual software, because we model the entire thing for a smaller subset, but it works, we cover essentially almost everything that is in C99. We cover almost everything. There are some parts that is still under work. But if any type of qualifier appear a function argument, it's the same thing that we do as assignments. So formal parameters, they are bound to arguments just like the right side of assignment are bound to left side of assignments. Is that what you're saying?
Yep.
Okay.
Thank you.
Hi. So did you find in your analysis that missing macro definitions ever misled what you determined?
Yes, macros are a terrible problem. So, so the thing is, if a macro is, if an unexpanded macro, it turns out to be valid C syntax, like a function-like macro or function object-like macro, we'll just understand that as a function, right? And we'll type that as a function. Of course, if the unexpanded function is not valid, then we can't do anything. But we do have some support like for project-specific macros in which you can already register in the software itself the expansion of that macro. For example, DLL export or decal specifiers from GCC attributes. So this can be used to parse realistic projects, right? And this is essentially what IDEs do, because IDEs also don't have the information about unexpanded macros, because it would require the compilation options for each particular file. So we do something similar in that respect.
Okay, thanks.
Yeah, thank you. Can you take the rest of the questions offline? Thank you.
Thank you.